Well, welcome back. Hopefully we've got a real friendly topic tonight on factoring. So our first definition of factoring is to rewrite a quantity as an equivalent product. Now, the nice part about factoring, and we can put this as our second little note here, is that your factored answer must be completely equivalent to the original quantity. So you always know if you're correct because you can simply distribute or FOIL it out to see if they match. So our first goal is to rewrite each of the following as a product of an integer with a different binomial. So let's just review some terms. Our integer is a whole number, and a binomial is two terms. Remember bi for binomial. So let's take a look at this first one, 6x plus 12. You could say it's what integer times what two terms. Maybe you've guessed it already. I could say it's 6 times what two terms? Maybe x plus 2. Now, you can always check, like we said, if you just take this and distribute it back in, do you get the original 6x plus 12? So you always know if you're correct. And we are. So let's take a look at the next one. 3x minus 6. You would say it's what integer times what binomial? I'm going to say it's 3 times x minus 2. And again, a quick check, 3x minus 6. I've got two more. Why don't you pause it, you try it, and see if we get the same thing. Well, I'm going to say I can't divide both of these by 6, but I can divide both of them by 3. So I'm going to say it's 3 times some binomial. So I'm going to say if I want a 6x, I'm going to say that's 3 times 2x plus 5. And again, if you weren't sure, quick check, 6x plus 15, and it works out. The second one, again, I couldn't choose that first term of 6, so I had to get a little creative there. I'm going to say I could use a 2 and say it's the binomial 3 minus 7x. So what we did, and we just didn't have a name for it, is we pulled out the greatest common factor. So again, let's label that in our notebook, the greatest common factor. We're looking for the greatest or the largest that can be divided into both terms. It's usually referred to as the GCF, greatest common factor. So we're pulling out a GCF. And when we say pull out, we're dividing it out. Now, it doesn't just have to be an integer like we did on the last example. It could be an integer and a variable. For example, if I have 3x squared plus 6x, if I just focus on the numbers 3 and 6, the greatest number that can go into those is 3. And now if I focus on the variable x squared and x, the greatest amount I can take out of both is x. The reason it can't be x squared is there's not an x squared to take out here. The greatest I can take out of both is x. And then I'll bracket in what's left. If I divide this by 3x, I'm left with x plus 2. And again, a quick check will tell me 3x times x is 3x squared, and 3x times 2 is 6x. Let's go on to this 20x minus 5x squared. So again, start with the number. Look for a GCF of the number. I would say I can pull out a 5, and if I check those variables out, I'm going to go with an x again. So what would be left? Well, 5x times 4 would be 20x, and 5x times 1x would be 5x squared. Now when we write that single x, we don't need to put the 1 there. It's implied that by you writing an x down, there is one of them. So same idea. Why don't you try the next two, pause it, and see if we get the same thing. Good luck. So in this first example, I'm going to pull out a 5 and an x and say this is the same thing as doing 2x plus 5. And again, a quick check. 10x squared plus 25x. On this last one, I'm going to pull out a 10. Notice I can't take an x out because this term doesn't have an x. So I'm going to say that's 3x squared minus 2. Now, let's try this. When if you didn't see that they had a 10 that you could pull out? Maybe you thought you could only pull the 5 out. And you had 6x squared minus, 4. The only problem is this is not done being factored because there's still a GCF here. So if you do it this way, it's okay. You just have to factor again. Now you can say you can also take out the number, we have a 5 outside, and we can also divide those by 2, so I'm going to go pull that 2 out, and I would multiply those and say I would get 3x squared minus 2. And then my final answer, 5 times 2, would be that 10, and my 3x squared minus 2. So if you don't pull out the greatest, you're just creating a little more work for yourself, and you'll have to factor again. So really try to find that greatest common factor. In the next set, we're going to rewrite each of the following trinomials as a product of its GCF and another trinomial. Okay, so again, trinomials implying we have 3 terms, and we're going to pull out a GCF, and it still has to be multiplied by a trinomial. So taking a look at this first example, if I just focus on the numbers, I hope 2 is popping in your head as the GCF. How about the variables? I wouldn't say there is one because this term doesn't have a variable. So the only GCF I can pull out is a 2. And then I'm saying 2 times what would get me 2x squared? Well, x squared. 2 times 4x would get me 8x. And 2 times 5 would get me 10. And that's all we're looking for. We're just pulling out the GCF. In the next example, let's see. I could pull out a 5, I think. So I'm going to say 5 times what is 10x squared? 2x squared. 5 times what is 20x? Minus 4x. Now here's where people sometimes fall apart. Remember, you have to rewrite this as a GCF and a trinomial. You had 3 pieces. 5 times what is 5? 1. Make sure that plus 1 is there. If you started with 3 terms in here, you better end with 3 terms in here. Alright, same idea. Good luck, try those 2, and we'll compare in a few moments. Well, here are my solutions, and again, hopefully they match, and you can always check just by distributing this 4x back through. So it'd give me 8x cubed, check, minus 12x squared, check, plus 20x. On this pair, hopefully you had the same thing. That would be 6x cubed, plus 15x squared, minus 21x. Our next little section is called Conjugate Multiplication. So let's get that titled in the notebook. And go ahead and we'll write down our formula and box it in. Here's the conjugate multiplication pattern. X minus a times x plus a is simply x squared minus a squared. So let's think about distributing that out. X times x would be x squared plus ax minus ax, and a positive times a negative, well, negative times positive is minus a squared. And you'll notice things cancel when you have the same amount and one's positive and one's negative. Then they cancel each other out. So I'm left with this x squared minus a squared, and that's the conjugate multiplication pattern. You'll notice it's the first term squared basically and the last term squared. So our next section says rewrite each as a product of a conjugate pair. So get used to saying that word conjugate. Maybe say it out loud a few times for yourself. Rewrite each product as a conjugate pair. So what times what is going to get me x squared minus 9? Well, hopefully you're saying x and x. Now I need my 2 middle terms to cancel, and I need them to multiply to a 9 at the end. So I'm going to go with 3 and 3. They have to be the same, otherwise they won't cancel. And one would have to be a plus, one would have to be a minus. And again, how do you quickly check if you're right? X times x is x squared, minus 3x plus 3x, so they're going to cancel their opposite signs, and then a minus 9, a positive times a negative. All right, let's try the next one. 4x squared minus 25. Okay, so the first 2 terms have to make the 4x squared. What's jumping in your head? Hopefully 2x and 2x. The last 2 terms have to make negative 25, and I need the middle terms to cancel, so I know they have to be the same. So I'm going to go with 5 and 5. Now if I need them to cancel, one has to be positive and one has to be negative. And again, they have to multiply to a negative 25. And again, quick check. 4x squared minus 10x plus 10x, they cancel, minus 25. All right, just like before, you've got the next 2, see what you come up with. And the more you practice these and pause these, the better you'll be. So remember, they had to be the same. So you can't use 4 and 1. You've got to use the same numbers. So I'm going to go with 2 and 2. 1 gets a plus, 1 gets a minus because I need the middle terms to cancel. And if I want an x squared, I'm going to go with x and x. On the next one, I need to get a 16. So again, I can't use 1 and 16. I need them to be the same. 4 and 4. 1 gets a plus, 1 gets a minus. Doesn't matter the order. To get the 81, the same numbers would be 9 and 9. And to get the x squared, that would be x and x. So I'm going to go 9x and 9x. And again, a quick distributing or foiling or tabular method would get you the same answer. So again, let's make another note in our book here. Most people refer to the conjugate multiplication, that's what we just did, as the difference between two perfect squares. I'm sure you've heard that term back in Algebra 1, the difference between two perfect squares. Some teachers might call it dots, difference of two squares. Some people say the whole name. And some people call it conjugate multiplication. It's all the same thing. So let's just review our perfect squares before we go any further. A perfect square is what you get when you multiply any number times itself. So for example, if I said 1 times 1, that means my perfect square is the number 1. 2 times 2 is 4. So 4 is a perfect square, but 2 is not. 3 times 3 is 9. So 9 is a perfect square, but again, 3 is not. Can you do the rest of them? 4 times 4, I could get 16. 5 times 5 is 25. 36. 49. 8 times 8 is 64. 81. 100. 11 times 11. 12 times 12. Pretty much, if you can get up to 12, we're in good shape. Then you can kind of play with your calculator if you need to. Now, how about variables? This might get a little trickier. Some numbers are pretty straightforward. But let's try some variables and jot the rules down here. X times x equals x squared. So x squared is a perfect square. X squared times x squared, when you multiply, you add exponents. So x to the 4th is a perfect square. X cubed times x cubed is x to the 6th. So I want all this written in your notebook, how you're getting these perfect squares. So x to the 6th is a perfect square. Could you keep going? Of course. X to the 4th times x to the 4th. So x to the 8th is a perfect square. Okay, these numbers are not, but these are my perfect squares. Alright, so you just have to notice when it's conjugate multiplication or the difference of two perfect squares. And it's fairly simple. Everything should be a perfect square if it's a difference of two perfect squares. So let's take a look at this first example. X squared minus 1/4. Well, x squared is a perfect square because x times x is x squared. 1 is a perfect square because 1 times 1 is 1. And 4 is a perfect square because 2 times 2. So this is a difference of two perfect squares. So, or conjugate multiplication. So you just ask yourself, what times what is x squared? Well, x times x. Remember, the middle terms cancel, so 1 gets a plus, 1 gets a minus in conjugate multiplication, or difference of two squares. And now, what fraction times itself is going to get you 1/4? Well, what times what is 1? 1 times 1. And what times what is 4? 2 times 2. So that's exactly how I would factor or use the difference of two perfect squares or conjugate multiplication. So even though they're fractions and they look scary, they're not that bad. Let's try the next one. Do I have the difference of two squares? Well, what times what is 25? 5 times 5. 1 gets a plus, 1 gets a minus. X squared over 9. Well, what times what is x squared? X times x. And what times what is 9? 3 times 3. And again, you can always check by distributing it. I get 25. When I multiply, that's really 5 over 1, so I'm going to get 5x over 3. And then when I multiply these, I'm going to get 5x over 3. But notice the signs were different, so they cancel. Minus, the top is going to give me x squared, and the bottom is going to give me 9. So again, you can always check. Alright, you've got 2 to try on your own. Pause it, good luck, and then compare. All right, here's my answers. And again, I'm just saying what times what is 4, what times what is 81, what times what is x squared. Same thing with 49 and 9, so you can check my work here and check my work here. All right, the next quick thing I want to talk about is the bear trap. So get that down. What if I said x squared plus 4? Can this get factored as a difference of two perfect squares? What do you think? So you're saying, okay, I need somebody times somebody to get x squared. Well, that's easy, x times x. I need somebody times somebody to get 4, and that's easy, 2 times 2. Why can't it be? Well, think about this. You have to multiply to a positive 4, which means your signs have to be the same. Either they both have to be positive, or they both have to be negative. Now, we said in conjugate multiplication, or the difference of two perfect squares, you need opposite signs. So this is not possible. Okay? It is not possible because to get a positive 4, you have to have the same sign. In the difference of two perfect squares, you have to have different signs for them to cancel out. Another big hint is it's called the difference of two perfect squares. In math, what is the symbol difference? Difference is a subtraction sign, and the second I saw a plus sign here, I know it can't be factored. So it's actually done at x squared plus 4. Our last group is called factoring completely. So again, let's title that nicely. Factor until it can't be factored anymore. And that's the word completely is the big hint there. Just keep factoring until it can't be done anymore. Usually means there's at least 2 steps. Sometimes more, but at least 2. So another rule of thumb is generally the first term is a GCF. So let's look at this example. Right off the bat, I don't have perfect squares. 5 is not a perfect square, and 20 is not a perfect square. But I do have a GCF. So I'm going to pull that GCF of 5 out and say 5 times what gets me x squared minus 20? Well, I would say x squared minus 4. Now I'm not done, and my hint was to factor completely. Inside of my parentheses, I have a difference of two perfect squares, or conjugate multiplication. Make sure you keep the 5, and now factor this guy. What times what is x squared? It's a difference, so one gets a plus, one gets a minus, and what times what is 4? 2 times 2. So let's box this in. You have to have that 5 in front. That's got to stay along for the ride. Because remember, in the end, you've got to get 5x squared minus 20. And if you didn't bring that 5 down, you would never get it. Let's try the next one. 28x squared minus 7. I'm going to start with my GCF. I think I can pull out a 7. So I'm going to say 7 times what binomial, and I know it's a binomial because I started with one, gets me 28x squared minus 7. Well, I'm going to say that's 4x squared minus 1. Now, the completely makes me think I got to do something else, which I do. Perfect square, perfect square, perfect square. So I'm going to rewrite my 7. Say what times what gets me 4, 2 and 2. X and x get me the x squared. One gets a plus, one gets a minus, doesn't matter which one it is. And then 1 times 1 is 1. So I've got a total here of 7 times 2x plus 1 and 2x minus 1. All right, you've got it figured out by now. You've got the next two. Pause it and see how you do.